In 1856, a man named Bernard Riemann, who we will call Ree, invented 5 ways to find the area under a curve. These sums are not trapezoids. No. These 5 ways are easier, and easier is the most important thing in calculus. In other words, Riemann invented 5 ways to find the definite integral, and although sometimes inaccurate compared to other methods, using these methods gives you close approximations to the definite integral as you increase the number of rectangles you use.
You can remember these 5 summations by the acronym LORUM. Lower, drawing the rectangles according to the lowest point on the rectangle interval, as you can see in the graph. Upper, drawing the rectangles according to the highest point on the rectangle interval. Left, drawing the rectangles according to the most left point on the interval. Right, drawing the rectangles according to the most right point on the rectangle interval. And finally, midpoint. Draw the rectangles according to the midpoint on the rectangle interval.
In the following problems, you will be evaluating different definite integrals and finding the best way to take the sums, including finding over and under approximations. Ree, the mad mathematician, will be stuck in the math problem and wants to escape the deadly graph. If your sum is an over approximation, Ree will flee to safety. If it is an under approximation, Ree will be trapped forever. Your goal is to help Ree escape so he can make more fun math problems. In order for Ree to never get trapped again, you also need to figure out which summation is the closest to the real definite integral.
Okay, so in this first problem, we're given the integral x squared plus 3 in the interval 0 to 3, and finding the upper, lower, middle, left, and right sums using 3 rectangles to determine if Ree will escape the graph or be trapped. So first, we're looking at x squared plus 3, and we know this is going to be a parabola, which is increasing as it approaches infinity and also increasing as it approaches negative infinity. So we know the shape of the graph is concave up. Okay, so next we're going to find the base of the rectangles. And this is given by b minus a over n, which is the number of rectangles that it wants you to find, which is 3 in this case. So we're going to do 3 minus 0 over 3, which is 1, and that will be the base of the rectangles. Okay, so first we're going to find our left Riemann sum. So we're going to use the leftmost point. In this case, we're going to use the values at 0, 1, and 2 as the height of our rectangles. Okay, so first for our left Riemann sum, this height right here is 3, so 3 times 1 is 3. And then for this one right here, it's 4 times our base of 1 is 4. And this one is going to be 7 times 1 equals 7. So 3 plus 4 plus 7 equals 14 for our left Riemann sum. So for the right Riemann sum, we're going to use the value at the rightmost point in that interval. So we're going to use the value at 1, 2, and 3 for this right Riemann sum. So first, our length at 1 is 4, which is going to make our area 4. For the second one, this is 7, so it's going to make the area 7. And for the last one, it's 12. And all those added up equals 23 for our right Riemann sum. So for a midpoint Riemann sum, we're going to be looking at the midpoint between each interval. So for us, it's going to be at 1/2, 1.5, and 2.5. So the value at 1/2 is 3 1/2. The value at 1.5 is 5 1/4. And the value at 2.5 is 9 1/4. which equals 17 3/4 for our midpoint Riemann sum. Since the function is increasing, we can see that the left Riemann sum is actually going to be equal to the lower Riemann sum because the leftmost point is the lowest point in that interval. And for our right, it's actually going to be the upper Riemann sum. So those numbers are going to be the same because it is concave up and increasing on this interval.
So we can calculate that when we have a left approximation or a lower approximation on the graph x squared plus 3, we will have an underestimate or an under approximation, which means re will be stuck. Taking the right and upper approximations will leave you with an overestimate, which means re will escape. So, because this graph is increasing and concave up, right and upper approximations will leave you with an overestimate. So, any graph of this nature will have these same features, including left and lower approximations being underestimates.
So from plugging the definite integral into my calculator and finding the exact one, it is 18, which means the midpoint sum is the closest because it is 0.25 away from the exact integral.
Even though the midpoint Riemann sum is the most accurate, it is also the hardest to determine whether it is an over or underestimate. You can do this by calculating like we just did, or looking at the graph features. Because this is increasing and concave up, the midpoint Riemann sum will be a bit of an underestimate as proven by our calculator. If it is the opposite, it will be a bit of an overestimate.
So for the second problem, we have to evaluate the integral of to the x from 1 to 4. And we have to find upper, lower, midpoint, right, and left to determine if we will skip the graph or be trapped underneath. So first, in order to find the base of our rectangles, we're going to take our interval b minus a, which is 4 minus 1, over the number of rectangles, which is 6, which equals 1/2. It's going to be the base of our rectangles. So first, looking at the left and lower Riemann sum, since this is concave up, you're going to want to use a calculator to find these values since it is exponential and a bit more difficult to calculate by hand. But you're going to find the values at 1, 1/2, 2, 2.5, 3, and 3.5 for the left and lower Riemann sum. So for upper and right Riemann sum, you're going to be looking at the values at 1.5, 2, 2.5, 3, 3.5, and 4. So lastly, for our midpoint Riemann sum, you're going to be looking at the values at 1.25, 1.75, 2.25, 2.75, 3.25, and 3.75. So for the second problem, our left and lower Riemann sum are going to be 16.9. For our right and upper Riemann sum, it's going to be 23.9. And for our midpoint Riemann sum, it's going to be 20.1. So from plugging to the x into the calculator from 1 to 4, I found the exact definite integral is 20.1977, which is the closest to our midpoint sum, 20.1.
Through this problem, we can observe two things. Number one, that the midpoint sum, the majority of the time, if not all of the time, will be the most accurate sum to use to get the closest answer. But also, the more rectangles you use, the more accurate your sum is going to be. We used 6 rectangles in this problem, which gave us less than 0.1 away to the actual answer of the definite integral, whereas in the last problem, we used 3 rectangles and were a little bit larger of a margin, 0.25 away from the actual answer. You guessed it, right and upper approximations would allow Reed to escape this math problem.